The PRESS program is one phase of a cooperative US-Japan program on large-scale testing of structures for earthquake and wind resistance. This particular
Este programa en particular involucró una investigación que analiza los diferentes aspectos del comportamiento sísmico del hormigón prefabricado. Pero por otro lado, la fase final de esta prueba es tomar en cuenta cómo es el comportamiento de una estructura real a la que se le conoce como superensamblaje, dado que es una estructura de 5 pisos como un edificio común que se lo pueda encontrar, donde se busca que encajen todas sus partes y asegurarse de que se provea de un edificio real, para que de esta manera seamos capaces de analizar o de tener partes reales del diseño de la estructura. Es tratar de hacer que las deformaciones en los lugares donde la estructura tiene que doblarse y ceder se hagan y sucedan en las conexiones entre las diferentes piezas. Ahora, si se está construyendo en un molde que va a ser colocado para una estructura de hormigón, no hay ningún tipo de conexión entre estas piezas discretas y realmente no se tiene una opción como se está trabajando con estructura prefabricada, porque concentrando las acciones inelásticas en las conexiones, que es bastante diferente de la forma en que se ha diseñado el hormigón prefabricado en el pasado. Se ha cambiado esto en la actualidad, pero ahora la pregunta es, ¿cómo saber si se puede utilizar una edificación después de que ha ocurrido un sismo? Eso no es lo que la gente obtiene ahora cuando compra los edificios, puesto que cualquier ingeniero se lo dirá después de un análisis, pero existen sistemas que se están probando que en realidad dan un paso más allá y están tratando de minimizar el daño estructural en caso de un sismo. Para probar estos nuevos sistemas de herramientas se ha hecho una estructura nunca antes vista en Estados Unidos y es conocida como la fase 3 de la prueba PRESS y se someterá a una prueba final en una instalación única en la Universidad de California. Como herramienta de ingeniería, el objetivo de esta estructura es tratar de unir muchas de las conexiones individuales que se han desarrollado durante los últimos 5 a 6 años y se han probado como conexiones individuales durante estos mismos años. Además, la intención es que se intente juntarlos en una estructura y luego cargar la estructura como si realmente estuviera teniendo estos acontecimientos sísmicos, siendo realmente dañada para ver cuáles serían las deformaciones y desplazamientos reales. Asimismo, ver cómo trabajan todas las piezas en conjunto y por otro lado, las pruebas en la dirección norte-sur se probarán 4 sistemas de pórticos diferentes que consisten en columnas y vigas, como está mostrando a continuación, mientras que en la dirección este-oeste se probará un sistema de muros de corte. Este sistema de muros es un ejemplo clave del uso de postensado para la resistencia sísmica. Se puede ver cómo los cables son extendidos a lo largo de toda la estructura. Además, las fuerzas sísmicas son transportadas por las paredes, que se puede pensar en estas paredes o muros como un naipe gigante que transporta la fuerza sísmica de la estructura a través o en conjunto de los cables de postensado, que asimismo se pueden pensar como enormes bandas de goma que son hechas de acero de muy alta resistencia. No están hechas de caucho, pero se comportan de la misma manera elástica, por lo que al colocarlos en la pared a través de un tubo, un conducto, este acero hace que formen parte de la estructura y se sujeta la pared contra el suelo. Los sistemas híbridos y pretensados del edificio y sus conexiones en la parte oeste de la estructura tienen un pequeño espacio en el extremo de la viga y la cara de la columna, ya que en la parte inferior de este espacio se llena con lechada para proporcionar contacto entre la viga y la columna. Además, están conectados por acero postensado que corre a lo largo del edificio, sujetando el marco en la parte superior e inferior de la viga, como se está apreciando a continuación. Y a través de la columna también se corre este cable, excepto en un tramo corto entre la viga y la columna. Cuando la viga se mueve lateralmente en un terremoto, los espacios en ambos extremos de la viga se abren y cierran por igual, manteniendo las dimensiones del sistema del pórtico por encima de las conexiones de espacio. En este lado del edificio, las conexiones modelan un sistema que es similar al que se usa en la construcción convencional de fundición y colocación, como es el prefabricado. En este caso, la conexión solo utiliza barras de refuerzo que se inyectan con lechada, excepto en un tramo corto en la interfaz de la viga con la columna. Esta conexión está incluida imitando al uso actual de las conexiones de vigas prefabricadas. Y por otro lado, el edificio usa un concepto innovador llamado el pretensado no adherido, que consiste en tener un acero interior que está adherido a la estructura. Entonces, si se tiene una unión entre viga y columna, esta unión se separa, hace que el cable de pretensado gane mucha fuerza y entre en el rango inelástico, pero cuando se cierra de nuevo ya perderá parte de su pretensado. Por lo que, por otro lado, si el cable no está adherido, no se encuentra en el mismo aumento de fuerza, haciendo que no tenga un comportamiento no lineal y por lo tanto no se perderá nada de la resistencia previo a un evento sísmico. Además, se han realizado una serie de experimentos que han demostrado que esto es cierto en el ensamblaje de vigas y columnas, pero esta es la primera vez que se ensamblan en un sistema estructural completo, por lo que en esta prueba se han utilizado variantes del concepto básico de Presley. Las conexiones en los pisos inferiores se puede apreciar que consisten de vigas que utilizan torones de postensado no adherido y estos se tensan tanto en la parte inferior como superior y se inyectan con lechada, excepto en la parte final de la viga. Cuando la viga se mueve lateralmente en un terremoto, la barra de refuerzo produce energía disipada y los torones permanecen elásticos, lo que hace que el pórtico vuelva al centro después del sismo. Mientras que en la parte superior encontramos vigas pretensadas, que consisten en colocar acero pretensado en el interior de las vigas y con hormigón adherido solo en sus extremos. Siguiendo el proceso, a medida que el pórtico se desplaza lateralmente, el acero no adherido permanece elástico y ayuda a que la estructura vuelva a centrarse como lo han hecho los anteriores sistemas mencionados. Todos estos diversos sistemas se han integrado cuidadosamente en una estructura a escala para que pueda caber en el laboratorio de pruebas, porque a pesar de ser un laboratorio inmenso, este tipo de edificación no cabería en si se lo hace de una manera más grande. Es por eso que se ha tomado esta optativa y finalmente podemos apreciar cómo se lleva a cabo este proceso de ensayo.
Testing is to study the structure's response to earthquakes. But how are the effects of a seismic event? Testing is to study
at each elevation. And then we began setting the floor slabs. And the crew's done very well so far as to get every piece in with all the necessary parts.
The core objective of the testing is to study the structure's response to earthquakes. But how are the effects of a seismic event created inside a lab? Here at UCSD, the cadre of seismic design and testing experts has the ability to employ a technique called pseudo-dynamic testing to faithfully recreate the effects of an earthquake.
The reason that we can slow the earthquake down in this form of testing and still have valid results is because we ensure that the sequence of displacements that we put on to the building is the same as would happen to the structure if it was tested at a faster speed, in other words, at the correct loading rate for the earthquake. And damage is related to displacements rather than forces or anything else. So if we take it to the same displacements that would happen in the real earthquake and in the same sequence, then we get the correct levels of damage. In fact, we get slightly more because it's more severe on a building to hold it at the large displacements for a period of time than it is just to achieve it for a fraction of a second and take it off. So it's slightly conservative, but it is realistic.
The simulated seismic events for the pseudodynamic process are derived from a select variety of actual earthquake records, among them the 1940 El Centro earthquake record. These records are then modified to ensure that the structure is thoroughly subjected to the required levels of seismic intensity and beyond. The mechanical means which will bring the earthquake record back to life are the actuators.
For this particular test, we have 10 different actuators. We have 2 at each floor level. They come in different varieties with strokes from plus or minus 6 inches for the first floor, all the way up to plus or minus 24 inches for the top floor. The actuators on the first floor have a 165,000 pound load capacity. Those at the top floor have a 220,000 pound load capacity. This actuator here, for example, can push with a load of 165,000 pounds. That's something around the weight of like a 727 or a 737 jet aircraft. The actuators are kind of unusual in that we have this combination of really large forces, but yet we're able to control them down to very, very small displacements on the order of 1,000th of an inch. In the control room during the test, there'll be 5 of us. There'll be me, and I'll be controlling the actuators and monitoring the health of the actuators and the data acquisition systems. There'll be Sri. He's monitoring what's actually going on during the test and conferring with Dr. Priestley to make decisions about what we're going to be doing next, whether the structure is behaving as we want it. There will also be 2 graduate students, Jim Conley and Stefano, and they will be doing close to real-time analysis of what's going on in the structure. The test actually takes place in several intermediate tests, and between those tests, these 2 graduate students spend a lot of time helping us make decisions about what we want to do on the structure next.
The structure is ready for testing. 12 years and countless hours of design and preparation have gone before. The testing begins. Time-lapse footage compresses the process. The team watches closely, monitoring the activity of the actuators as well as the response of the structure. A graphic display shows the amount of force the actuators are exerting to produce the target displacements. As it is subjected to the first loads, the structure makes evident its response to being displaced.
I think it's probably the pins, I guess, is it?
Something slipping in the pins, I think, yeah. Okay, just hold it there for a minute.
The structure successfully withstands the design-level earthquake requirements.
We are right on.
Now it is crunch time. It will be taken to the extreme. The displacement will be equivalent to an earthquake which might occur once a millennia. The top floor of the building will move over 11 inches from center, or over 22 inches back and forth, much greater than the movement which occurred, or over 22 inches back and forth, much greater than the movement which occurred in only a few seconds in El Centro in 1940. A few seconds which had devastating consequences. Here, the duration is a matter of hours, yet the structure is actually subjected to more stress than in that real seismic event. As the test progresses, displacement becomes clearly evident. The flex plates in the walls bend as designed. The top floor moves further and further from center, the columns clearly leaning. At the height of maximum displacement, the researchers clamber over the structure. Floor by floor, they inspect and record evidence of the displacement's effect, so they can later correlate it with the data gathered by the instruments.
Yeah, we got the torsional crack in the floor.
You got a torsional crack now?
In the floor, yeah.
0.1 millimeter. Look at you, too excited about that.
Think fire?
Time-lapse footage reveals how the pseudodynamic testing process eerily recreates the earthquake. The building experiences the first seismic wave and then suffers a remarkable displacement and continues to sway with subsequent seismic waves. But the walls, frames, and floors stand, and by all accounts, don't even approach a loss of integrity.
The lack of damage has surprised even me. It's been less than I expected, so it's just been great. It's a superb test.
It's amazing to me how little damage, how little distortion, things are able to move the way they're supposed to without anything bad happening. And if you had this kind of an earthquake and of course you're going to run out into the street probably when it's over, you're going to come back in and see architectural and interiors type damage, but the building structure is going to be fine and you'll be able to go right back to work. And I think that's amazing for an earthquake this size on a building.
There's no doubt that the level of shaking represented by what we've put onto this building is well above the design levels for buildings in California.
But it seems that the performance we're seeing at this displacement is actually much better than I'd even dreamed. Some of the very critical connections seem to be performing absolutely perfectly, and places where I expected to see some cracking in the concrete, not dangerous, but at least cracking, we don't seem to be seeing it. So the building is doing just astoundingly well, as far as I can see. And I'd be very happy to live in a building like this in a big earthquake. What else can I say?
Next in line for the battery of tests are the 4 frame systems joining beams and columns that make up the east and west sides of the structure. After shakedown and calibration, the researchers are ready to get underway. The first tests take the structure up to a level 2 earthquake record, equal to events which might occur once every 50 years. The various framing systems are performing well. This time-lapse footage clearly shows not only how flexible concrete can be, but it once again illustrates how effectively the pseudodynamic process recreates the dynamics of the earthquake record. The researchers then take the structure to the 500-year seismic event. The top floor is displaced about 10 inches from center, giving the structure a tilt which is clearly evident, even to the casual observer. The structure easily survives the design level tests. Nigel Priestley comments on what is yet to come.
The next step in our testing, which we'll start next Tuesday, is to take the structure to levels of seismic displacements which are significantly bigger than expected in the design earthquake. The structure is designed for a maximum drift of 2%. What we want to do now is to take it to 3% drift, so a margin of safety of something like 50% above the design displacement, and see how it performs at that level. Assuming that it performs well there, we'll then take it up to 4% drift, or twice the design level. If it's still standing and intact at that stage, we'll call it a day, because we won't be able to apply displacements any bigger than that. We've run out of capacity in our actuators.
At that 3% drift, or 50% above the design displacements, the top floors are pushed close to 12 inches from center. At this level of displacement, well beyond what the framing systems were designed for, the various systems start to show their superior performance characteristics. The pre-tensioned beams and hybrid systems perform extremely well, without an increase in significant damage.
So it's close to 7/16 inch crack, and I think as I said earlier, it's all concentrated here, and you don't get any crack on the beam at all. So it's performing as it was expected.
As in all good research, the team wants to probe the limits. They follow their plan to take the structure to 100% greater displacement than the design level. The top floor will be displaced 18 inches from center, the kind of displacement which might occur once every 2,500 years. The test gets underway. The researchers watch closely, monitoring the actuator systems and state of the structure. At the extremes of displacement, the team inspects the structure.
There's quite a lot of relative movement there.
Diagonal shear crack on the joint, the exterior joint.
These welds all look okay.
HE3S, one of the bottom rebar fractured.
Outside of it.
Outside one.
The test continues. As the strains increase, the structure responds with eerie creaks, cracks, and booms. The structure is reaching phenomenal displacement. The joints, where by design the stresses and damage are concentrated, start to show some effects. Concrete spalls, crushed at the joints between columns and beams. Rebar under tension snaps like immense rubber bands. Then, on the second full cycle of drift, something happens. Judiciously, the test is halted. The structure is allowed to settle.
Yeah,
I could fire those guys up and let them come to zero load.
Let's do that.
All right.
As far as, the test's completed now.
The team has taken the test far beyond the limits of expectations, into a realm which few structures have entered, and remained standing. After the structure is cleared of apparatus and instrumentation, project scientist Sri Sridharan takes the first step to understand what really went on in the test structure, revealing the effects of the seismic stresses as well as the performance and resilience of the designs.
The only damage that occurred to the wall system during the wall direction testing was just pulling of cow concrete in the corners here. You could just patch it up if you wanted to, and you're ready for the next earthquake. There were some minor cracks that we marked here that opened up and they closed when we removed the load. On this side we marked all the cracks, and we'll take a look at it on the other side. You will see there is no damage that you could visibly see. Right now we are looking at a hybrid joint system where the column to beam connection is established with unbonded post tensioning, similar to what we have seen in the wall system. You could see there's no damage to the joint region where the maximum forces are transferred through. The damage what we see here at the top and bottom, in a design level earthquake, we will not see any damage like that. Part of the reason why we see this damage was that we took the structure to much larger displacements. At one point we moved the top of the column by 18 inches. And that's the reason we see some damage, and again this is not structural, so we could easily patch up this damage as well. We are now looking at a pre-tension frame connection. Unlike the other precast system that we have looked at, here the beam is continuous, which contains the joint as well, so it runs from one end of the frame to the other end. In this system, the crack was supposed to develop between the joint and beam, even though the whole piece was constructed as one segment, and that's exactly what happened during the test. And you can see the crack develop right at the interface, and the crack opened up all the way to 3/8 of an inch for the maximum earthquake load being imposed onto the building, and now it's almost completely closed.
The success of the PRESS program has been a defining event, which promises to propel seismic engineering, design, and science forward.